Welcome back to our quantum series, The Whole Story. Today, we're diving straight into a foundational explainer on the double-slit experiment. And look, we are tackling an absolute cornerstone mystery of the universe here. We're going to unpack how probability itself literally becomes physical reality and why the very act of knowing something fundamentally changes the world around us. It's wild, so let's get into it.
I want you to start by just completely abandoning your intuition for a second. Ask yourself, is the fundamental nature of reality a particle or is it a wave? I mean, do things exist as solid, localized little clumps, or do they exist as continuous, spreading ripples? It really feels like it has to be one or the other, doesn't it? Before we shatter those expectations completely, let's just firmly establish what classical physics expects. If you throw standard particles, things like stones or bullets, through two parallel slits, they hit the wall behind in distinct clumps, right directly behind the slits. But if you send waves through, like water ripples, they pass through both slits, they overlap, and they create what we call an interference pattern. That's a series of alternating high and low points. This is our classical baseline. Particles clump, waves interfere. Easy enough, right?
So here is our roadmap. We are going to hit the setup that broke intuition, compare classical versus quantum predictions, and see exactly how measurement kills the fringes. Then, we dive into the true paradox, the delayed choice eraser, check out some modern lab realizations, and finally, reveal reality's true nature.
Chapter 1. The setup that broke intuition. Let's look at the foundational anomaly that shook classical physics right to its core.
Now, what's incredibly fascinating is what happens when we send individual solitary particles, like single electrons or single photons, through the two slits, strictly one at a time. Classical physics says, hey, they should form two distinct clumps. But when you track the progression as individual particles hit the detector one by one over time, they miraculously build up a wave-like interference pattern. It's like a single particle is somehow interfering with itself. There's just no way that makes classical sense.
And honestly, this isn't just some quirky lab result we can brush off. The legendary physicist Richard Feynman famously stated that this phenomenon contains the only mystery of quantum mechanics. It's the absolute core of wave-particle duality. The particle arrives like a discrete bullet, but its probability of arriving absolutely anywhere is dictated by a wave.
Chapter 2. What classical reasoning would predict. Let's explore this massive conflict between our math and Mother Nature.
In normal classical reasoning, if an event can happen via two paths, you just add the probability of path A to the probability of path B. Simple math. But quantum reasoning doesn't use standard probabilities. It uses probability amplitudes. Think of these amplitudes like literal waves in a swimming pool. If a high crest meets a low trough, they flatten out. They entirely cancel each other out. And that cancellation is exactly what creates the dark, empty spots in the interference pattern. The math literally tells us the particle explores both paths simultaneously. Chapter 3. Which way information kills fringes? Okay, here comes the big plot twist. What happens if we try to cheat the system? This is the classic observer effect. Say we place a detector, really any kind of measuring apparatus, right at the slits to figure out the which way information of the particle. We want to know, did it go left or right? The very moment we do that, the wave-like fringes completely vanish. Once we know the path, the particle instantly stops acting like a spread-out wave and snaps right back into acting like a classical bullet.
This is the absolute strangeness of our reality. Unobserved, we get interference fringes. Observed, we get clumps. The particle's behavior entirely depends on the type of measurement performed on it. Niels Bohr called this idea complementarity. Simply put, nature dictates that we absolutely cannot have both the wave behavior and the precise particle path at the exact same time.
But why does this matter so much? Because it's not physical clumsiness destroying the pattern. It's not the detector physically bumping the particle off course. The math shows us that the loss of the interference pattern is directly correlated to binary entropy. That means the precise mathematical measure of information gained by the observer is what causes the change. Acquiring data fundamentally alters physical reality.
Chapter 4. Delayed choice and quantum eraser. If your head isn't spinning quite yet, it's about to. Let's push the boundaries of time.
Physicist John Wheeler proposed a brilliant thought experiment to test if the particle somehow knows it's going to be watched in advance. Step 1, the photon enters the setup. Step 2, a random choice is made to either extract the path information or leave it ambiguous. But here's the crucial part. This choice is made after the photon has already passed the first split. It's already well inside the system. Wheeler perfectly captured the mind-melting implication of this.
Because the choice of how to measure the photon is made after it has entered the apparatus, we're dealing with a strange inversion of time. Our choice now, in the present, unavoidably determines whether the photon traveled one route or both routes in its past. Think about that for a second.
The proof is right there in the real-world data. When researchers actually perform this experiment, and they even take it a step further by recording the which-way information and then actively erasing it before correlating the data, bam, the wave pattern is literally resurrected. Erasing the path information mathematically brings the interference fringes straight back from the dead.
Chapter 5. Architectures and Modern Realizations. You might be thinking this is all just theoretical philosophy, right? Well, let's look at the engineering.
We have come a really long way from Thomas Young poking holes in window blinds back in the 1800s. To test these quantum paradoxes today, labs use mind-blowing technology. We're talking electron biprisms, specialized down-conversion crystals that perfectly split single photons into two entangled twins, right up to custom CMOS chips that manage 1 million frames per second just to catch single electron arrival times.
In a modern interferometer used for these delayed choice experiments, a single photon is split. It's sent along two entirely distinct optical paths, and then a ridiculously fast electro-optical modulator decides at the absolute last microsecond whether to recombine the paths or leave them separate. And the scale of these setups is just staggering. In a landmark 2007 experiment we're referencing today, the paths were 48 meters long. The random choice of whether to observe the path was made by a quantum random number generator separated from the photon's entrance by such a huge distance that no signal, not even a signal traveling at the absolute speed limit of the universe, the speed of light, could possibly warn the photon about the measurement. It's a true space-like separation.
Chapter 6. What the double-slit really says. Let's pull this all together. After over a century of testing and pushing the boundaries of technology, what does this actually mean?
Here are your major takeaways. First, probability amplitudes are not just math tricks on a chalkboard. They are physical realities that interfere with one another. Second, complementarity is an absolute, unavoidable rule of nature. But third, and honestly most importantly, the sheer availability of information dictates the physical outcome. It's not about human consciousness looking at a computer screen, it's about whether the universe has permanently recorded the path information. If that information exists, you get clumped particles. If the information is absent or erased, you get waves.
Which brings us right to the edge of the quantum abyss. I want to leave you with this final thought to chew on today. If the mere availability of information is what forces physical reality to take a definite shape, who or what is observing the universe? Thank you for joining me on this explainer, and definitely keep questioning the reality around you.